Hi there, my name is Ben Rasmussen. I'm a software engineer, and this is Containers from a Cruising Altitude. This presentation is originally created for a conference called Nebraska.code, which takes place in Lincoln, Nebraska every year, but I wanted a generally distributable video format as well. This presentation does not provide the how to convert your application into a containerized application, but is more for the purpose of preparing you to do research on how you want to do the conversion. And specifically, I want to talk about virtual machines versus containers and some of the containerization tools available to you when you do want to perform the conversion. The motivation for this is a couple of years back, I and a couple of other devs at the place I was working at were tasked with converting our legacy monolith application into containerized microservices. And none of us on the team had really ever used containers before. We didn't really know what container softwares were out there. We'd heard of Docker and we ended up using it just because it was the most popular. But it wasn't until after the project that I got to reflect and wonder, what else is out on the market for us to use? What were some of our options? So this presentation is to give a little bit of a look into that. We're going to start with virtual machines and containers. And many people already know what virtual machines are, but I wanted to start there because it will give us a good baseline for what containers are as we move into containers and some of the containerization softwares. So a virtual machine is essentially a computer inside a computer or an operating system inside of an operating system, just kind of depending on how you look at it. And the VM's job is to abstract the physical hardware away, and that allows us to turn a single server into multiple servers, or a single computer into multiple computers. So in essence, every virtual machine is going to believe it has its own hardware. So every virtual machine will think it has its own hard drive, its own RAM, etc. So every virtual machine is going to have its own operating system, and along with that, all of its own binaries and libraries, where the binaries essentially are just executable applications and libraries are support code for the binaries. Every VM is going to run completely separate from the other VMs, and a virtual machine operating system can be of any type. It doesn't have to match whatever host it's running on. So if I'm running a Windows server, I can run a Linux virtual machine on it as well. So what manages and monitors virtual machines? If you're looking at the picture on the right, you might have a little bit of a guess here. The answer is hypervisors. Hypervisors create and run virtual machines. And on the previous slide, when we talked about a virtual machine abstracting away the physical hardware, it's actually the hypervisor that's performing that emulation. So the hypervisor's job is to act as a median between the virtual machine and the host. So if the virtual machine wants to write to disk, for instance, it's going to tell its kernel that it wants to write to disk at a virtual address. The hypervisor is going to receive that request and translate the virtual address to an actual physical address on the hard drive that can be written to, and then pass it off or perform the write as needed. There are two types of hypervisors. There is a Type 1 hypervisor, known as a bare metal hypervisor, and there's also a Type 2 hypervisor, which is known as a hosted hypervisor. So Type 1 hypervisors, bare metal hypervisors, these are going to run directly on top of the host's physical hardware. So there's not going to be a traditional operating system such as Windows involved. They tend to be very secure and very isolated. Part of the reason for that is because they don't have an operating system with all the vulnerabilities associated with an operating system. And these tend to be used in data centers because they are very highly performant, in part because there's no bloat from an operating system and device drivers. So if they need to take a request, a system call from the virtual machine, they can perform that request directly on the hardware. And some examples, Xen, KVM, Microsoft's Hyper-V, those are all bare metal hypervisors. Type 2 hypervisors are the hosted hypervisors, and these are going to run as an application on a host operating system. And they're going to utilize the host operating system's system calls. So going back to my example earlier, I have a Windows machine at home and I want to run a Linux virtual machine on it. So if I'm running on my Linux virtual machine and I want to perform a disk write, that system call is going to go to my Linux kernel, The Linux kernel is then going to pass it off to the hypervisor. The hypervisor is going to take the Linux system call and convert it to a Windows system call, and then hand it off to the host Windows operating system, and the Windows operating system will perform the write then. Obviously, with all of those steps, the VMs kernel to hypervisor to host kernel, we're introducing latency. And so type 2 hypervisors tend to be slower than type 1 hypervisors. These are going to be the types of hypervisors you're going to run on end-user machines like at home for development purposes. You're not going to run these in production. And a couple of popular examples, VMware Fusion and VirtualBox. So moving on to containers now. A container is actually the runtime of a predefined application image. And a container's job is to emulate the host operating system. So each container is going to believe it has its own operating system. It's going to do this by sharing the kernel of the host operating system. And the kernel is the part of the operating system that deals with the hardware. So when you make a system call to perform a write to your hard drive, the kernel is generally going to be what's taking that system call and scheduling the write. The application image that then becomes the container will only contain the software needed to run the application. This means that you tend to get a very consistent environment. So if I develop an application in Python 3 and I want to distribute it, I can ensure that Python 3 is the only version of Python that's deployed with my application, and I don't need to worry about, for example, Python 2 existing in the environment and messing up my runtime. Containers also tend to be very lightweight because they, again, don't have an entire operating system. They're just the application needed. And containers run using a container engine, similarly to virtual machines running using a hypervisor. So there are two types of containers. There are application containers and system containers. We're not going to talk much about system containers. As a developer, they don't really pertain to a lot of the universe that we're in, but I wanted to mention them just for sake of completeness. An application container is generally what most people think of when they think of a container. You run a single application or a single process, and it's generally considered an anti-pattern to run more than one process. So if you were trying to run a web application with a load balancer like Nginx in front of it, in the virtual machine world, you might deploy both Nginx and your web application on the same virtual machine. In the container world, you're probably going to split those out into two separate containers. Application containers also tend to be disposable. So if you're upgrading versions of an application, generally you're going to just destroy your old versions and stand up new versions. Application containers are broken out into two pieces. You have the image and the runtime. Some popular image specifications are the OCI, which is the Open Containers Initiative, and we're going to talk more in depth about that in the next section, and ACI, which is the Application Container Images, which is becoming more of a legacy specification. And a couple of popular runtimes. Docker, probably everyone has pretty much heard of that, and Rocket, which is a little less common, but I believe probably about the second most popular container runtime. System containers, just to breeze over this again, it doesn't apply too much to what we're going to be talking about from here on out. They are very similar to virtual machines. As opposed to application containers where you only have a single process running, system containers are going to run multiple services and processes. Just like virtual machines, system containers are going to be useful for maintaining fleets of systems. So if you want 20 CentOS systems, you can use system containers for that. And a couple of runtimes you can use for that are Linux, LXD, and systemd nspawn. So images. Both virtual machines and containers are based on images. And they share some of the same concepts, but they do have some differences. So virtual machine images are prepackaged operating systems and all the binaries and libraries associated with it. And that tends to make them very, very large. Container images are prepackaged applications and only contain the code needed just for that application. So they tend to be very small. Virtual machine images don't really have a central repository. There are some more popular destinations, like I think VirtualBox has a big library of virtual machine images, but there's no real de facto place to go for your virtual machine images. Containers, on the other hand, have the Docker Hub. This is an unofficial repository that it seems everyone has kind of flocked towards to store their images. So Python will have officially licensed Python images stored in the Docker Hub. And you can think of the Docker Hub kind of like NPM is to JavaScript or Maven is to Java. They're not officially licensed repositories, but everyone seems to go there for their information. Virtual machine images are just flat archived file systems. Container images are layered change sets of a file system. So you'll start with nothing, and then you'll add one file in as a layer, maybe Python 3, and then as a second layer, you'll add in your application, so on. And by doing this, you can get very efficient build times, because if you need to change, if you have 10 layers, for instance, and you need to change something in layer 7, you only need to rebuild layer 7, 8, 9, and 10. And you don't have to rebuild the entire container image. So a quick review of virtual machines and containers. Virtual machines abstract the hardware, and all virtual machines believe they have their own hardware. Application containers abstract the operating system, and all containers believe they have their own operating system. Virtual machines tend to be more secure because they are more isolated from one another. They have their own entire operating systems they're using. They don't have to share resources with one another. Application containers trade some of that isolation for performance. They tend to be very, very fast because there's nothing sitting in the middle between the container and the host that needs to translate calls. So if you make a system call, you're going pretty much directly to the host's kernel. Virtual machine images tend to be very large in size. They're measured in gigabytes generally. They're a full operating system, lots of bloat with that. Application containers, their images tend to be very small in size. They're normally measured in megabytes, and they contain a single application and only what's required for that application. Lastly, virtual machines are host independent. So if I have a Windows machine, I can run a Linux virtual machine without any issues. Application containers are host dependent, and they are dependent on the kernel of their host. So if I want to run a CentOS container, I must be running on a CentOS host. Likewise, if I want to run a Windows container, I have to be on a Windows host. Our next section will be about container specifications, and specifically the Open Containers Initiative